This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today's paper, Out of the Shadows, Exploring a Latent Space for Neural Network Verification, proposes a novel approach to neural network verification using a latent space. Let's start with the core challenge. What are the limitations of current state-of-the-art neural network verification algorithms?
Current methods often rely on reachability analysis or abstract interpretation, conservatively enclosing the set of possible outputs. This conservatism, stemming from over-approximating nonlinearities, leads to inconclusive results, especially with large networks at high-dimensional intrits. Branch and bound techniques mitigate this by recursively splitting the problem, but this can explode the computational complexity exponentially.
The paper introduces a latent space to address this. Can you elaborate on the concept of a latent space in this context and how it's constructed?
The latent space is built upon a novel interpretation of projection-based set representations like zonotopes. A zonotope is viewed as a shadow of a higher dimensional set. The propagation through the network only alters this shadow, leaving the underlying higher dimensional set, the latent space, unchanged. Input and output sets are thus shadows of the same latent space, enabling constraint transfer.
How does this constraint transfer improve verification efficiency? Can you walk us through the iterative refinement process?
The iterative refinement transfers output specifications back to the input space. This allows us to iteratively reduce the input set, focusing only on potentially unsafe inputs. We use Proposition 2 to formalize this refinement, enabling the removal of provably safe input regions. This significantly reduces the number of subproblems in a branch and bound procedure.
The paper mentions the use of zonotopes. What are the computational advantages of using zonotopes compared to other set representations?
Zonotopes allow for efficient computation using only matrix operations. This is crucial because it enables significant speedup through GPU acceleration, allowing for parallel verification of entire batches of subproblems. Many other advanced set representations, while potentially tighter, lack this computational efficiency.
The algorithm integrates this refinement into a branch and bound procedure. Can you describe the key steps involved in this procedure, highlighting the role of the latent space at each stage?
Algorithm 1 outlines the process. First, the output set is enclosed. Then, the intersection with the unsafe set is checked. If non-empty, falsification is attempted using a set-based approach derived from the latent space. If falsification fails, the input set is refined using Proposition 2 and split to further reduce conservatism. This iterative process continues until verification or falsification is achieved.
The evaluation section compares the proposed method with top-performing tools from VNN-Comp24. What were the key findings of this comparison?
The results show competitive performance, often matching or exceeding the top tools on several benchmarks. This suggests the latent space approach offers a significant improvement in efficiency and scalability. The detailed results are presented in Table 1, showing the percentage of solved problems for various benchmarks.
The paper also includes ablation studies. What insights did these studies provide regarding the design choices of the algorithm?
The ablation studies validated several key aspects. The set-based falsification method proved superior to alternative approaches. The iterative refinement, especially the layer-wise approach, significantly reduced the number of subproblems. Finally, the use of GPU acceleration with larger batch sizes dramatically improved the runtime. These results are summarized in Table 2.
How does this work compare to existing iterative refinement techniques in neural network verification?
Existing methods often involve refining bounds using linear programs or counterexample-guided abstraction refinement. Our approach differs by directly refining the input set based on the transferred specification, avoiding the need for hyperparameter tuning or solving expensive optimization problems. The latent space allows us to leverage dependencies between propagated zonotopes, simplifying computations.
What are the limitations of this approach? Are there any specific types of neural networks or specifications where this method might struggle?
While the results are promising, the effectiveness might depend on the specific network architecture and the complexity of the unsafe set. Highly complex networks or specifications could still lead to a large number of subproblems, even with the refinement. Further research could explore more sophisticated splitting heuristics or alternative set representations within the latent space framework.
The paper mentions the potential for counterexample extraction. Can you elaborate on how the latent space facilitates this?
If verification fails, the latent space allows us to trace back from a boundary point of the unsafe output set to a corresponding point in the input space. This provides a candidate counterexample which can be further refined or verified. This is described in Section 4.2.
What are the future research directions stemming from this work?
Several avenues are open. Exploring more advanced set representations within the latent space framework could improve precision. Developing more sophisticated splitting heuristics could further reduce the number of subproblems. Applying this approach to different types of neural networks and safety specifications would also be valuable.
The paper emphasizes the use of matrix operations for GPU acceleration. How crucial is this aspect to the overall performance gains?
The use of matrix operations is absolutely critical. It allows us to leverage the parallel processing capabilities of GPUs, significantly accelerating the computations involved in both the zonotope propagation and the refinement process. Without this, the performance gains would be significantly reduced.
In summary, this paper presents a compelling approach to neural network verification. The use of a latent space for iterative refinement offers a promising direction for improving both efficiency and scalability. Thank you for this detailed explanation.